Okay, let's get started with chapter 5 then. So, first up, electric charge. Electric charge is a property of matter that can either be negative or positive. Usually when we talk about negative charge, we refer to electrons, and positive charge, we refer to protons. Well, there are more ways, but you'll learn about that in chapter 7. So let's look into the properties of charge first. Like I said, negative means electrons, positive means protons. Second is that they are quantized. This means that the total amount of charge is always going to be a multiple of the basic unit, which is coulombs. So any object, if it's charged, like let's say this object here is negatively charged and it has a charge of 1 coulomb. This here is a multiple of the base, the basic unit, as I said, which is 1.9 times 10 to the power of, sorry, just give me a second, I need to look at the power up again, 10 to the minus 19 coulombs, not 1.9, 1.6 times 10 to the power minus 19 coulombs. Now the third property of charge is that charge is conserved, meaning like energy, it can neither be created nor destroyed. The amount of charge both before and after will remain the same. Now these properties of charge, you just need to know them. I've never really seen a case where they ask you to describe the properties of charge, but just keep them in mind. They can prove to be helpful. Now Coulomb's law. Coulomb's law states that the force experienced between two charged objects is proportional to the charge of the objects and inversely proportional to the radius or the distance between them squared. And it's times by a constant k, which is Coulomb's constant. So what I mean to say is, if we have two charged objects, let's say we have one here that's negatively charged and another one here that's positively charged, and this has the charge of, let's say, Q1, this has the charge of Q2, and the distance between them, this distance, let's label that to be R. Now the force experienced between these two charges will equal to, the force will be equal to K, which is Coulomb's constant, times the charge of this charge over here, this charged object over here, then the charge of this charged object here, Q2, divided by R squared. That is Coulomb's law. If they ever ask what Coulomb's law is, you can either say this out, in case of a definition question, say that it's proportional to the charge of the objects or inversely proportional to the distance between them squared, or you can just write out the equation. Now this constant over here can also be written as, sorry, not F, K, Coulomb's constant, equals to 1 over 4 pi E naught, and this over here is the permittivity of free space. Or the permittivity of a vacuum. Just write that down quickly. might have spelled it wrong, but okay. So the K, Coulomb's constant K, and the permittivity of your vacuum or permittivity of free space is given in your data booklet, so you can refer to them easily. Now, moving on. Electric field strength. So now, if you have a charged object, whether it's positive or negative, it will have an electric field around it. Let's take a negative charge, for example. So a negative charge will have some kind of electric field around it. Usually we draw inwards pointing arrows for an electric field by a negative charge because we talk about the motion of a positive charge over here, because opposites attract. So the positive charge will be attracted towards this negative charge over here. Yep, I am recording this. I'm actually using QuickTime on my computer because Craig doesn't really record the screen. It just gives an audio recording. But thank you, Semi-Sweet Potato, for adding the Craig, I guess, as a backup. Well, let's continue then. So when we talk about the electric field by this charge, the electric field strength, that is the electric force per unit charge experienced by a small test positive charge, can be given by E equals to F over Q, because it's the force over the charge, the force per unit charge. So if we have, let's say, a small positive charge over here, just take that to be positive, and because it faces a force going inwards towards this negative charge, it's attracted towards it, the electric field will be the force over the charge. Now, there's another way you can write electric field. If you remember earlier, we defined the force to be Coulomb's constant times the charge of the two particles. So we take the charge of the small test positive charge over here to be Q, small q, and let's take the charge of this big negative charged object over here, the one that's creating the electric field, to be big Q, so that we can make the difference between them. And let the distance between them be r, once again, r squared. So this distance from here to here is r squared. Now let's bring force in over here. So I'll write it over here because there isn't enough space there. E equals to K large Q small q over r squared all over q. Now since we have small q over here and small q over here, they cancel each other out, giving us another equation here, kq over r squared. So now you can use either this or this equation if you're ever asked to find out the electric field of a certain charged object. Now moving on. Current. Current is simply the rate of flow of charge. Now current can be defined by two equations. One is the change in charge over the change in time, and the other one is the current equals to the product of the number of electrons in a unit area, the electron drift speed, the cross-sectional area, and the charge per electron. So just to write it out a bit clearly, it might be a bit too small on my computer. So I equals to change in charge over change in time, Similar to our velocity equation, because velocity is the rate of change of displacement, here we have the rate of change of charge, or the rate of flow of charge. So it's just change in charge over change in time. And current can also be given by number of electrons, n, electron drift speed, v, then cross-sectional area of the region where it's traveling through, a, and the total, the charge of a single charge carrier. So now we can use this in case if we want to talk about the current flowing through a wire. Let me just draw a small wire over here. So if you want to, if let's say there's a potential difference, I'll get to what a potential difference is a little later. So just think of potential difference to be something that causes a current to flow through. Now there's a current flowing through this from the negative end to the positive end. And if you want to calculate the current over here, you can either use the change in charge over the change in time, or you can use NVAQ, where n is the number of electrons present in this, v is the electron drift speed, which will be given in the question, and I think it's also in the data booklet. A is the cross-sectional area, which means this area over here, and Q is the charge per charge carrier. And since in this case it's an electron, we know that it's going to be 1.6 times 10 to the minus 19 coulombs. Now the unit for current is amperes, simply given by A, which is the equivalent of coulombs per second, as we can see from here. Now to continue. Potential difference. Potential difference is the work done per unit charge to move a point charge from one place to another. So potential difference can be given by work done W over charge Q. So let's say we go back to the wire over there, as I'd drawn earlier. And you have an electron moving from here all the way down to there. Now the potential difference across this wire will be given by the work done over the charge that's transferred, which in this case is 1 electron. Now we have the electron volt. Now the electron volt is the work done when a charge equal to an electron is taken across a potential difference of 1. So 1 electron volt is always equal to 1.6 times 10 to the power minus 19 joules. This is in the data booklet, so you don't have to remember it. You just need to remember the definition of electron volt, which is the work done when a charge equal to an electron is taken across a potential difference. And with that, we're done with 5.1, the first part of chapter 5. Now, before I continue, is there any question? Okay. Just to make this clear, the attractive force between the repulsive force, yeah, it is the same. The attractive force is equal to the repulsive force for two same point charges. It just depends on the signs. So if you have a positive and a negative, then in that case it's attractive force. If it's a negative and a negative, it's repulsive, or positive is repulsive. The value will still be the same regardless of the signs of the charge. Now, is that all? What exactly is permittivity? So permittivity is how easily an electron or a charge can pass through a certain medium. For I equals to NaVq, could you repeat what each letter means? Okay, so in I equals to NaVq, I stands for the current, N stands for the number of electrons in the medium you're talking about, A is the cross-sectional area, or whatever it's traveling through. V is the drift speed of electron, and Q is the charge per carrier, not the total charge, the charge per carrier. Alright, then let's move on to 5.2, heating effect. So when electrons are traveling through a medium, like let's say a conductor, or for example a copper wire, they suffer through inelastic collisions with the atoms in the medium, which makes them lose energy in the form of heat. So if we visualize inside a conductor, let's assume this is a really zoomed in version, and you have the molecules present over here, and you have these tiny electrons that are moving through. Occasionally what happens is the electron actually collides with this atom and releases heat as energy. So this is what is resistance. Just want to make sure. All right, yep. This here is resistance. So resistance is the potential difference across a conductor over the current that's flowing through. That's how you quite literally define the resistance equation. Or another way to look at resistance is how easy or difficult it is for charge to flow through a certain medium. And like I said earlier, resistance can be simply calculated by resistance equals to voltage over current. Now, we have things known as ohmic resistors. So ohmic resistors refer to the kind of resistors or conductors in which the current flowing is proportional to the potential difference. What this means is if I have let's take a bulb this time instead of I'll just quickly draw a bulb. Something like that. It has a bottom over there, and then the filament. Yep, let's say there's a bulb, and let's assume this bulb over here is an ohmic resistor. What this means to say is that if I supply this bulb with various different currents, so now let's put a potential difference against current graph. So what I mean to say is no matter as I keep changing the amount of current I supply into this bulb, the change in potential difference or voltage will be the same. It will be proportional. So you would expect the graph to be a straight line. Trying to draw it as straight as I can. Yep. It will look like this. The increase in current will be proportional to the increase in voltage. However, as you change current and you get a different looking graph like this, let's say, or if you get something that's curving upwards, then that's a non-ohmic resistor. Now resistivity. Now resistivity is a constant that's used for for a certain material to show how easy it is for charge to flow through that conductor. Now you can use resistivity in order to help you calculate the resistance of a material. The resistance of a material can be calculated by R resistance equals to resistivity rho, that's rho, not a P. I tried drawing a rho but didn't work out, times the length over the cross-sectional area. So now from here you can tell this is one relationship you should know. The resistance of a certain material is proportional to its length, meaning as you have a longer resistor, its resistance will increase, and inversely proportional to its cross-sectional area. So if you have a thicker resistor, its resistance will decrease. You should keep that in mind. Oh yes, and I think I forgot to mention, the unit for resistance is ohms, which also is voltage per amperes, but I don't think you'll ever have to refer to it like that. Just remember ohms. Now, electric power. Electric power is the work done over a certain amount of time by a current. Now, power can be given by voltage times current, but how do we really arrive at that? Let's take a look into it. So like I said, power is work done over a certain amount of time by a current, right? So let's write out power first as we know it. Power equals to work done over time, right? So now we know the work done. If you remember earlier, potential difference equals to the work done per unit charge. So which means work done equals to charge times potential difference. So we get QV over T. Now notice one thing, we have Q over T over here. This is the same as current. So we end up with voltage times current. That's how you get power equals to voltage times current. Note in questions sometimes you'll have to substitute in current using the equation resistance equals to voltage over current. You may have to replace either voltage or current with either V equals to RI or I equals to V over R depending on the question, because they won't necessarily always give you the current or the voltage. Instead they give you the resistance. So just remember to make in such substitutions if you ever get a question like that. Now calculating the total resistance in a circuit. So you have two kinds of circuits when you depending on the arrangement of the resistors. So now let's just draw out a circuit. So you have a cell over here and you have a resistor over here. I'll just draw one resistor like that and another resistor over here. Right. So when you have something like this where they're right adjacent to each other or they're in the same flow, this is known as a series connection. So when you're calculating the total resistance of two resistors in series, the total resistance, which I'll label as RT or R total, is equal to, let's say the resistance of this is R1 and this one is R2, equal to the sum of these resistors. So R1 plus R2. Now if I have another resistor over here like this with a resistance of R3, the total resistance will now be R1 plus R2 plus R3. Now let's look into the other one, which is a parallel circuit. So let's say now we have a resistor over here, and then it branches out over here, resulting in another resistor. And now let's say this is R1 and this is R2. Now in this case the total resistance will be 1 over RT, or the total resistance is equal to 1 over R1 plus 1 over R2. Now whenever you're calculating total resistance for a parallel circuit, remember first you do 1 over each of the resistors, sum them up, and then you have to do the inverse of them, because 1 over RT equals to this sum over here. Quite often people do forget to do that, just keep that in mind. Now we have Kirchhoff's laws. So we have first law of Kirchhoff, which says that if current splits into a parallel circuit, the input current must equal the output current. What this means to say is, if I have a current coming in over here, a current of I. And now as it goes over here, some of the current goes here, some of the current goes here. When the current comes back over here, after going through these two branches over here, this current must be I. That is Kirchhoff's first law. Now Kirchhoff's second law states that the input voltage will be equal to the sum of the potential difference across all resistors. What this means to say is, if we have a potential difference over here of V, and we have these two resistors over here, let's just, for the sake of simplicity, let's just say the current over here is I1 and the current in this branch is I2. V must equal to R1 I1. Just put a bracket to show that these two are being, you take the multiple of these two times R2 I2. And we're assuming that there's no resistance in the wires, or the resistance in the wire is negligible. Alright, let's move on. Oh, next up is 5.3. So before I continue, any questions? You would say the resistance of the wire is the resistivity of the... Alright, I think you're answering a question here, so is there anyone else asking? Thanks a lot, semi-sweet potato. Can you explain an example of two voltage sources and the current's direction? So I assume what you mean by that is, if you have two cells in a circuit, so let's say like this, and just add in a resistor over there. Oh, looks like we got some lag. So in this case, both the terminals are facing each other, so you have a current that's resulting outwards. But I think what you mean to say is, like in a case where you have, let's say, opposite facing cells, like cells in which the terminals don't match each other, you have the negative facing the negative and the positive facing the positive. In that case, the direction of the current depends on the potential difference generated by these two cells. So if this cell has a potential difference greater than this cell, the conventional current, the resulted conventional current will be this way. But however, if this cell has a greater potential difference than this cell, then the conventional current will result this way. Does that help? Oh, Adam. So what they mean by sigma V equals 0 and sigma I equals 0. So when they say sigma V equals 0, so let me draw out a better circuit. So what, sorry, I forgot a resistor. Let's just take one resistor over here, for example. So let's say this has a potential difference here, and we take this as positive potential difference, and then we have a current flowing out over here. Now the potential difference lost over here can be given as minus Ri. So what they mean to say is, according to Kirchhoff's second law, plus Vi minus Ri must equal 0. That is what they mean by the first one. Oh, you're trying to look for a different example. All right, then in that case, how about you send me at the end of the session and I'll go over it. For now, let's move ahead. Does that sound good? All right. And Adam, do you understand what they mean by sigma v equals 0? All right. Let's keep moving on then. Now on to electric cells, which is fairly short. So first off, the first thing you need to know about an electric cell is that any kind of electric cell converts energy from one type of energy to another form of energy. So in this case, you have some other form of energy being converted to electrical energy. So let's take an example of a battery cell. A battery cell contains chemicals in them, and what essentially happens is a redox reaction occurs in that chemical cell, which produces a potential difference, resulting in electricity or electric energy being formed. Now let's move on. Wait, did I miss something? No. All right, I think I didn't describe what EMF is. Electromotive force. I may have missed that out, so I'll just go over that real quick. Sorry, just give me a second. Yep, electromotive force. Yeah, I plan to go over it over here. So electromotive force, sorry. Yep. So electromotive force is the potential difference that is initially being produced in a cell. So it is, for those of you who do chemistry, if you remember the equation that we have over there, that is E cell. Electromotive force is the E cell, not electromotive force, electromotive force is the E cell, which is the theoretical value of the theoretical potential difference that should be produced in a battery. However, in cells, because of how inefficient they are, you don't necessarily get the potential difference that should theoretically be there. So it can be taken as there is some kind of resistor in it, which we shall refer to as internal resistance, that results in, let's say, this whole region here is the cell, and that is the internal resistor, which leads into some potential difference loss in the cell itself. We always use small r when representing it, and whenever you have a cell, the potential difference that results from the cell, the potential difference from the cell will be equal to the electromotive force E minus the current produced I times the internal resistance small r. And that, I believe, should be all that is there for 5.3. Well, you also do have the concept of primary and secondary cells. This is the example that I was referring to earlier, and probably what Pascal was referring to as well. So if you have a circuit, let's draw a circuit over here with, let's say, a resistor over here and another cell like that. And this one has, let's say, a potential difference of 12 volts, and this one has a potential difference of 2 volts. In this case, the conventional current will flow from the one that has a higher potential difference, which is the 12 volts one in this case. And This one, the one with the larger potential difference, is always referred to as the primary cell. And then this one here is the secondary cell. And over here, Kirchhoff's second law is still observed. Let's say the current here is I and the resistance here is R. In this case, 12 minus 2 minus Ri, because still we have potential difference being used up in that resistor, will equal 0 by Kirchhoff's second law. This is always followed. Right. And you also have the concept of cells discharging. So a cell won't always be producing the same voltage. Otherwise, we could like use the same battery forever to, let's say, have our GBA running or a torch running for essentially forever. So the voltage produced from a cell against the time will always look something like this. Let's say it starts off over here. At first, the battery, when it's new, it produces a lot of potential difference, and then you have a period where it produces the constant potential difference, which allows your battery, any battery powered thing, to run, and then it suddenly dips down. This is the time over which the battery has been running. This here is the potential difference generated by the battery, and this is how you would always expect the shape to be. And also the rate at which this dips depends on the current. Like let's say this was when we had a 1 amp current running. If I have a 0.5 amp current running, it would look something like this. It'll take a lot longer to discharge, say 0.5 amperes in this case. And that's that for chapter 5.3. Weren't primary and secondary cells the one that can and cannot be recharged? Oh, let me check that again. Yep, you're right. Sorry, I made a mistake over there. Primary cells are those that can only be used once. So once it runs out, you cannot use them again. Meanwhile, secondary cells are the ones that can be recharged. Like an example of a secondary cell would be the batteries in your phone. You can keep recharging them and using it over and over again. But meanwhile, an example of a primary cell would be the consumable ones that you find in the market, the ones that you put in your torch or any other similar device. Is there any other question before I move on to chapter 5.4? That is magnetic fields, the last part of the SL syllabus for electricity and magnetism. All right then. Just wait for a moment. Okay then. Yep, I have already covered Kirchhoff's laws. I had done it a while back. Would you like me to go over it again, or do you think it's fine? Should I just move on? Okay, I'll just explain it quickly then. So you have two Kirchhoff's law, Kirchhoff's first law and Kirchhoff's second law. So Kirchhoff's first law states that when a current splits into parallel circuits, the input current must equal the output current. What this means is that if you have a circuit like this, I'll just avoid drawing the resistor. I'll just quickly draw a resistor. What it means to say is that if you have a current of I coming into these two parallel branches, and then they split out like that, and then when they come back out, this current over here that leaves these branches must be I. It must be equal to the initial current that goes in. Now, Kirchhoff's second law states that the input voltage will equal to the sum of the potential difference across all resistors in a circuit. So what this means is that if I have a cell over here going into a circuit where we have one resistor and another one, I'll just add it in, and you have a current that's coming to of I, and this battery cell over here has a potential difference of V, and you have resistors R1 and R2. V must equal to I R1 plus I R2, or the sum of V equals V minus I times R1 plus R2. I can just simplify it like that because it's a series circuit, will equal to 0, which is what I believe is in your data booklet. The sum of the potential difference over the entire circuit will equal 0. Does that work? Alright, cool. Let's move on to the last part then, magnetic fields. So anytime you have a current flowing through a wire, it automatically produces a magnetic field. And it produces it in circular shapes going outwards. So let's say I have a wire over here and then there's a current flowing through it. A current that's going, let's just say it's going upwards. So you have a magnetic field around it, which is towards a certain direction. I don't think my drawing's too great, but I hope that gives you an idea. This is around the wire, is what I was trying to draw, but I don't think it turned out like that. So, and what I mean by these field directions is that if I place a compass over here, a compass or a magnet actually, let's make it simpler. The north end of the compass will be pointing in the direction of the arrow. So if it's over here, it'll be pointing up. If I have it over here, it will be pointing that way. That's what the direction means. Now, how do you find the direction at which this magnetic field is? You use the right-hand grip rule. So the field in a straight wire, you take your right hand, put your thumb up, and you curve your fingers around the wire. So you have your thumb over here, and then you curve your fingers around it. Oh wait, that's a left hand, not a right hand. Sorry. So you have your thumb over here, then you have your fingers like that. Just trying my best to draw some fingers. Yep, a man of just 3 fingers. Your thumb will represent the direction of the current, and your finger, the way your finger points, is the direction of the magnetic field. Now if you have a coil of wires, let's say you have a coil of wires like this, the magnetic field is a bit different in this case. And over here, if you were to use your right hand rule, your fingers curling would represent the direction of the current in the coil. So let's say the current is going like this, going through over there, coming up, going down there, coming up again, and so on. So you'd have your fingers curling around over here to show how the current is flowing through the coils, and your thumb, which I believe is this way, is showing the direction of the magnetic field. And the magnetic field around a coil looks something like this. The arrows pointing that way. Like I said, because this is the direction in which north points and opposite poles repel, so therefore this side must be the north pole, this side must be the south pole. That here is an electromagnet. Magnetic flux density is the magnitude of a magnetic field at any given point. So in essence, it's similar to an electric field. So it's just how strong a magnetic field is at any point from a magnet. Now, when you have a charge moving through a magnetic field, the force experienced by the charge can be given by QVB sine theta. So let's draw out the case I'm talking about. Let's say I have a actually, it would be better if I do this. Let's say I have a horseshoe magnet, for example. A horseshoe magnet. This is the north, this is the south, and field lines point towards south. I have the field lines like that. And now let's say I have an electron, a small electron that's moving in like this. The force experienced by this electron, the force experienced by this electron from the magnetic field can be given by the force is equal to Q, the charge of the electron, V, how fast the electron is moving, B, the magnetic flux density over here, sine theta. Sine theta is the angle between the magnetic flux lines, or the line showing the direction of the magnetic field, and the direction in which the electron is moving. In this case, it's a right angle. So sine theta equals 1, it's just QVB. Or let's say if the electron was coming in like this, like that, then this angle over here, theta. That's what would determine the force experienced by the electron. So clearly the electron faces the maximum force as it goes perpendicular to the flux lines. Now if you move, now we have Fleming's discoveries. Let's say we have a magnet over here, and S, and it has field lines going like this, and you have a wire that's sending current through it. Now notice, if we have current that's flowing through it, that means electrons must be moving, and because there's some kind of charge moving, it experiences a kind of force. This causes the wire to experience a force and move, and it moves in a certain direction. Now in order to determine how it moves, I make use of something called Fleming's left hand rule. So you take out your hand, this time your left hand, you have your thumb, your index finger, and your middle finger. You keep them out, sort of like that. Sorry, that's a really bad looking hand, but just please bear with me. So now your thumb finger shows the direction of the force, the direction in which the force is. Your index finger shows the direction of the field. This is the direction of the field. I'll just put it as B. And this here is the direction of current, I. So now, if we look at the case we've been given over here, we have the field direction over here. Now if you align your index finger over there to the field, and then try to move your hand around so that you can align your middle finger to the direction of the current that's going upwards, and you'll find out the force is actually into the whiteboard. The wire will go down or into the whiteboard. That is Fleming's left-hand rule. Note, when I talk about Fleming's left-hand rule, you refer to the direction of flow of electrons. If it's for conventional current, that is the other way around, then you have to use your right hand. And now to determine the force of a current carrying wire in the magnetic field. So of this case over here, we use F equals to B I L sine theta. Once again, the angle at which it intersects the flux line does matter. Let's say this is theta. Yep. And I believe that's it for magnetic fields as well, but there's one thing I can add on. This is an interesting question. I've seen it pop up a few times. I'm not sure if it has come a few times in an exam, but it's been in 2 of my exams, so I guess it comes up fairly often. So now let's say we have a magnetic field. Note I'm drawing these. This means to say is that the magnetic field is pointing out of the paper, so it's coming towards us. I'll just draw a few like that. And let's say an electron comes in to this field over here, and it starts moving around in a circle. So we have an electron that's moving around in a circle. And they can ask you, let's say this is the center at which it circles, and it's circling around because remember the electron faces a force from the magnetic field, so it can move around in a circle. So now they can ask you to find out things such as the period at which this electron is moving. Now in this case, you should realize that the force that is exerted on the electron from the magnetic field will equal to the centripetal force, which means you can rearrange this to get QVB, because it's a lone electron going through here, not a current, equals to mv square over r. Now you have velocity on both sides, so I can get rid of the square. And let's make the radius the subject of the equation. R equals to mv over qb. So you can equate that to radius. Now if you want to find out the period from here, if you remember from, I haven't done a circular motion session yet, but in circular motion, and it's also given in the data booklet, we know that 2 pi r over v is equal to the period. Now if I rearrange this equation to get it in terms of r, let me see if I can. R equals to TV over 2 pi. So now let's bring this back over here. I'll just write it above. So we have TV over 2 pi equals to mv q over b, q times b. So we have velocity on both sides, can get rid of that. So we get period equals to 2 pi m over qb. And these values should have been given to you in the question. So now you should be able to, with no problem, find out the period if they give you such a question. So, do we have any questions? Well, flux density is in HL, but you need to sort of know what it is, because you have cases where you have to talk about magnetic field. So you just need to know the definition, not many calculations related to it for the SL part, I believe. Well, that's all from my part for today. Are there any questions that you would like to ask before I sign off for the day? Yeah, all right, Pascal, as you said earlier. Okay, bring it up. Let's try go through it together. From the SOCOS book, I see. Ah, I see this question. I think I've done it before. Let's go through it then. Calculate the magnitude direction. I believe it's the first question that you would like to get clarification on. 17a. So let's try go through it now. Let me first redraw this diagram. We have a cell over here. Okay. And then bridging out down. Oh, never mind. We have a few things over here. A resistor over here and another cell. Okay. That I believe is one part of it. It's point A, point B. Draw another branch out. And another resistor over here. Yep, so of course questions can get really tricky. 2 volts, 4 volts, 4 volts, all resistors are 4 ohms. 2V, 2V, 4V, R, R, R. Okay. Sorry, I shouldn't write R. I should actually put 4 ohms, 4 ohms, 4 ohms. All right. So now let's start by targeting each battery one by one so that we can find out the magnitude of the current that's coming. I'll start off with the one with 4 volts so that it's easier. So if you remember, according to Kirchhoff's second law, the sum of the potential differences must equal 0 at the end. Sorry, can you just give me a minute? I need to find the switch for the light. It's getting a little dark here. Okay, so now let's start. So 4. Now we want this to equal to 0 at the end. Let's trace out currents from here. All right. Let's label this current to be I. And now we have I splitting up. Actually, let's go the conventional current way. It's a bit easier that way in this case. Let's get rid of that. Sorry, I got rid of the wrong thing. We want this to equal to 0. Let's have a current of I coming over here. So now it's passing through one resistor, so we have some potential difference loss over there. The potential difference loss of 4I, which is the current that's going over here. And now it's splitting into 2 circuits. Now note over here, the resistance in this branch is equal to the resistance in this branch. Both of them have a resistance of 4 ohms. And we're neglecting the internal resistance of these 2 volts. But even in that case, they have the same internal resistance. So we can say that the current going over here is I over 2. Sorry for the really small I over 2 over there. This diagram is a little congested. So we have a current of I over 2 going over here. So let's go down this branch first. So we have I over 2 times 4 being used up over here, or just minus 2I. And see, our positive is going into a positive over here. So this is negative potential difference over here, minus 2. And we have the same thing happening over here, minus 2I, minus 2. And if we start looking into this, interesting. We actually end up with I equals to 0 from here, which is odd. I wouldn't expect that. Maybe I am making a mistake over here. Let's see. Let's try look through it again. Current equals to 0. That's odd. Well, let me try looking into the other ones first, whether the same thing happens over there as well. So let's have a different current going over here. I1. Actually, oh, I did? I see. Let me check that again. The middle battery is 4 volts. I see. That's why we're having a problem. Thanks a lot. I'm not sure who said that, but thanks a lot. 4 volts. Yep. That should fix things over here. Let's rewrite now for this branch over here. We have minus 2I from the resistor, minus 4 from this. That equals 0. We have this 4 that goes off. 4i minus 4i minus 2i minus 2i is minus 8i minus 2 equals to 0, giving us a current of minus 1 over 4, which means that it's current flowing in the opposite direction in this case. But that shouldn't be the case. Do you have the answers for this by chance? Yep, I can do another question. Let me try and get it. Oh wait, this is the Cambridge Books exam type questions, right? If so, I can get the answers now. Alright, it should be somewhere over here. Nope, not here. Where's the other one? Yep, here it is. So if I go to resources, test yourself questions. Wait, is it the test yourself questions or was it the other one? Exam style. Topic exam style questions. This is for topic 5. And let's get this. I believe these give the answers as well. So we can take a look at that. Question number 17. Here we go. Okay. Oh, I see. They made use of something different over here. They took the current coming out from the center cell. And the answers seem different as well. Okay. Let me try that again then. I'll bring this over here to refer to it. let's go from the center cell in that case. So we have a current going out over here and a current going out over here. Let's say this current here is X, this current here is Y. Right, I think that's what I believe they did. They took X and Y. Okay, so we have, let's take this direction first. 4 minus 4 times X plus Y minus 4 times Y minus 4 minus 4. Right, wait, hold on. What have they done over here? I see. What they have done is they've made this equal to the total potential difference in this circuit. That is 4 minus 4. Yep, that is what they have done. So we get minus 4x minus 8y equals to 0, which is minus x minus 2y equals to 0. Now if we take the other root, the total potential difference in this side is going to be 4 minus 2, which will equal to the potential difference used up first in this one. That's minus 4 x plus y, because you have both the currents going through over here, minus 4y once again. No, you have 4x this time, which gives 2 equals to minus 4x, sorry, minus 8x minus 4y. If we divide both sides by 2, we get 1 equals to minus 4x minus 2y. And if you run this in your calculator, you should get the answer. Yep, that is what it is. And you end up with the answers as the current in this direction, y, will be equal to 0.17, and the current in the other direction would be negative, and it's minus 0.34. Hopefully that makes sense. Or I'm sorry, I made a mistake at the start. Okay, cool. Okay, Saeem, go ahead with your question. Would you like me to answer the entire thing or just one part of it? Proton velocity. Oh, so you want part B and C. Okay. Well, actually, and E also. So do you understand of how part A works? Yep. Okay, that's good. So what is the radius of the helix? So what I assume they mean to say is this proton ends up in circular motion. Wait, no. Negative positive direction, C proton is on the CX Oh, it goes through circular motion, right? Yep. In case of circular motion, I think I did mention this a short while back. What you need to do is you need to equal the force to the centripetal force. And in this case, it's originally coming in at an angle, so you need to include the equation with the angle. So you need q v b times sine theta. And I'm pretty sure over here we have theta equals 30 degrees, so we can just take it as 0.5. And we equal that to mv squared over r, where r is the radius. So theta is 0.5. This velocity strikes off and we get rid of the square over here. And if you make r the subject, you should get r equals to mv over 0.5 qb, or simply just 2mv over qb. And I believe the other value should be given. That should allow you to find out what it is. And now once you've gotten the radius, you can just simply use the formula t equals to 2 pi r over v in order to find out the time period for the circular motion. Once you have time period, you can find out frequency, which I believe is what they're asking, how many revolutions per second. So just 1 over the time period that you find out using this equation. Does part C also make sense to you? Alright, cool. How fast is the proton moving along the field lines? Oh, right, you need with part E. Okay, you got it? Are you sure? Can you just explain A? Are you sure this is an IB question? I think it's a little more complex than that, because I don't think it's circular motion happening over here. What they're saying is that there's a helical path happening. So what they mean to say is that if we have the field lines over here, what it's saying is that the electron will go like that and sort of do some kind of a helical shape. I'm not sure what a helical shape is. Let's see what they're talking about. Helical path. Oh, I see. That's what they mean. Okay. So what they're trying to say is, in this case, if you have the field lines going up, they want you to explain why the electron comes like this and it goes in a circle while going in a general upwards direction. They wanted you to explain why that happens. That's because it's coming in at an angle, because of which it keeps going upwards. It isn't completely perpendicular that it starts going in a circle in the same spot, because it's coming in an angle that's going relatively upwards. It does move upwards in this shape, which is called a helical shape. Yeah, sort of like a DNA shape. Right, the helix, the double helix. Yep, my bio knowledge is not so good. Is there any other question that you would like me to clarify? Yeah. All right, in that case, I'll bring the session to an end now. Thank you all for attending. I hope it helped you.